When you look at a drop of a complex mixture, like blood, a pharmaceutical extract, or a cup of coffee, you're looking at a black box. Dozens, sometimes hundreds of individual chemical compounds are tangled together into a single uniform fluid. The challenge is figuring out exactly what those hidden components are and exactly how much of each is present. It is the definitive method for separating, identifying, and quantifying those mixed chemical species. This diagram outlines the entire architecture of an HPLC system. It maps a linear journey that starts here at the solvent reservoirs, pushes through high-pressure pumps, injects the sample, drives it through a tightly packed column, and finally passes it through a detector. We are going to walk through each stage of this journey. We will look past the physical buttons on the machine and explore the fluid dynamics and chemical interactions at play, so you understand how to protect your equipment from damage and ensure your data is perfectly reliable. By understanding the physics inside this exact machine, we can take that chaotic, mysterious mixture and force it to reveal itself as clean, actionable data. Step 1 begins with the mobile phase. This is the liquid solvent, often a mixture of water and organic chemicals, that physically carries your sample through the entire chromatography system. Looking closely at the solvent reservoirs, you'll see a sparger and an inlet filter. Before the liquid goes anywhere, it must be purged of dissolved gases and microscopic dust. Even a tiny air bubble can wreck the flow rates or create massive noise in your final detector readings. Once clean, the mobile phase enters the reciprocating pump. The packing material inside the analytical column is incredibly dense. To force liquid through that kind of physical resistance, this pump generates severe pressures, routinely up to 6,000 psi. The pulse damper then smooths out the mechanical strokes to ensure the flow remains perfectly steady. As the pump draws solvent, it can run in two different modes. If it pulls a single, unchanging mixture of solvent for the whole run, that's called an isocratic flow. If it actively changes the ratio of solvents over time, say starting with mostly water and gradually increasing the organic solvent, that is a gradient flow. Gradient flow is almost always preferred. By shifting the chemical polarity of the mobile phase mid-run, you force stubborn compounds to move faster, which sharply reduces the total time needed to finish the separation. Establishing this flawless, bubble-free, highly pressurized flow is the strict mechanical prerequisite. Without a stable mobile phase, the delicate chemical separations downstream will fail. Now we face a mechanical problem. We have a system running continuously at 6,000 psi. We need to insert a small liquid sample into that raging stream without dropping the pressure or exposing the internal tubing to the open air. The solution is a sample injection valve. This schematic shows the valve in the initial load position. In this state, the high-pressure mobile phase bypasses the injector entirely. This allows you to safely use a syringe to fill the holding loop shown here with your sample at normal room pressure. When you trigger the injection, the internal core of the valve is physically rotated. Instantly, the loop is placed directly into the path of the high-pressure pump. The mobile phase crashes through the loop, sweeping the exact volume of your sample straight onto the column. Because this valve switches paths in a fraction of a second, the sample enters the system as a tight, concentrated band. If it leaked in slowly, the compounds would smear out, making them impossible to read later. With the sample now in the flow, it hits the analytical column. This thick-walled stainless steel tube is where the actual chemical separation takes place. The inside of this column is packed solid with the stationary phase, millions of microscopic silica particles, usually coated with specific organic molecules. When our tight band of mixed samples slams into this dense matrix, a chemical competition begins. Molecules in the sample that are chemically attracted to the stationary phase will constantly grab on to the silica particles. They stick, release, and stick again, fighting their way through the column at a very slow pace. In contrast, molecules that prefer the moving liquid of the mobile phase will ignore the silica walls almost entirely. They wash straight through the gaps, rushing far ahead. The column acts as a chemical racetrack. It separates a uniform liquid into individual, isolated bands, purely by exploiting the different physical affinities each molecule has for the stationary phase versus the mobile phase. Because of those different travel speeds, the hidden compounds now exit the column one by one in single file. They immediately flow into the detector. Most HPLC setups use a UV-visible absorbance detector. This is a schematic of a Z-shaped flow cell, which acts as a small optical window located right at the end of the line. When only the pure mobile phase is running through the cell, a constant beam of ultraviolet light passes through the quartz windows and strikes the detector on the other side at full intensity. This creates a flat baseline reading. But when one of those separated target molecules finally enters the cell, its chemical bonds will absorb a portion of that UV light. The light hitting the sensor dims, and the machine registers the drop in intensity. That tiny, temporary shadow inside the flow cell is the exact moment the physical chemistry of the liquid is converted into a measurable electrical signal. This is a chromatogram. It is the final graph plotted by the computer based on those light intensity signals coming from the detector. The horizontal x-axis tracks retention time, how many minutes it took for a specific compound to travel from the injection valve to the detector. The vertical y-axis measures the strength of the detector signal, which tells us how much of that compound was present. The peaks clustered here on the left side, at lower retention times, represent the molecules that barely interacted with the column packing. They preferred the mobile liquid phase and washed out almost immediately. The spikes on the far right are the compounds that bonded heavily to the stationary phase. They required significantly more time and solvent to finally break free. For comparison, look at the bottom graph. This was run using an isocratic flow, a single unchanging solvent mixture, instead of a gradient. The later compounds took nearly 30 minutes to elute, spreading out into an overlapping mess that makes precise measurement extremely difficult. A successful run yields sharp, narrow, highly distinct peaks. When you achieve that, you've successfully operated the system, controlled the chemistry, and turned an unknown chaotic fluid into a complete quantifiable profile.